friends and physics loving people. I'm back again with another video on quantum mechanics, that is the use of time-independent Schrödinger equation for a spherical symmetric potential. We'll define what is a spherical symmetric potential, and then we'll see how the time-independent Schrödinger equation takes the form while using this kind of potential. And later on in the coming videos we'll show how the TISC can be solved for this kind of potential, and we'll take an example of hydrogen atom for the same. So let's proceed to see how the Schrödinger equation becomes for a spherical symmetric potential. The potential which we call a spherical symmetric potential is defined through the equation 1. We see here that the potential is no longer dependent on the direction, it simply depends on the magnitude of the distance from a fixed point. So whether it's classical or quantum mechanics, the motion of a particle in a spherical symmetric potential is immense important. For example, the motion of Earth around the Sun or the hydrogen atom problem in quantum mechanics are some of these things that which uses the concept of spherical symmetric potential. So what is spherical symmetric potential? Answer is that the potential which depends only on the magnitude of distance from a fixed point is the spherical symmetric potential, and it does not depend on the direction of the distance, it only depends on the magnitude of the distance, and that's why it's called to be spherically symmetric. It's symmetric in all directions, and that's why it is spherical symmetric. Now we'll use this potential to time-independent Schrödinger equation, and we'll find that the wave function can be separated into radial and angular part using the spherical polar coordinate system, and we'll see how the system three-dimensional system becomes a one-dimensional problem. So let's proceed to the next one. So this is the TISC. Usually we write for a three-dimensional case where nebula score is there, and then this is the potential. So in spherical polar coordinates, this R vector is replaced by the spherical polar coordinates r, theta and phi, and also the wave function u is also replaced by ur function as a ur and u, theta and phi. Now the nebula for u is now becoming as defined in the spherical polar coordinate system is like this: 1 by r del square ru del r square, then 1 by r square, this quantity with a u outside. Now this quantity within the bracket is now put as this capital lambda here, and so equation 3 is taking this form. So our Laplacian over the nebula square is now replaced by 1 by r del square ru by del r square plus 1 by r square lambda u. So here the lambda is an operator defined through this relation: 1 by sin theta del theta del divided by del theta, 1 by sin square theta del square del phi square. So this is one of the expression when we convert ourselves back to the spherical polar coordinate system. And also, since we have defined the potential as a spherical potential, so we'll see that this r is only dependent only on r. It is independent of theta and phi. The direction part of r vector is basically dependent on theta and phi, and since for spherical symmetric potential b is a function of only r, so it will not depend on theta and phi. So with all these things, equation 3 we can now with a method of separation of variables like this get the equation in this form. Simply the separation of variables where this capital R is a function of only r and y is a function of theta and phi, and we'll see later on that the equation can be separated out in terms of capital R and also in terms of y. So with these modifications, equation 3 and 5 and putting them in equation 2, we get a relation like this: 1 by r d to r small r capital R by d to r twice m x cross square e minus br, and which is multiplied by capital R and y, and then this part because of this part. And we can see in equation 6 that with one more simplification, that we can put a equal sign here, and in that sense it will be a minus sign here, and then keeping all the terms dependent on small r on the left hand side and terms dependent on theta and phi on the right hand side, we get a relation like this. For that, we are dividing this quantity by capital R and Y from left hand side as well as right hand side. Right hand side is always equal to 0. So dividing this quantity by R and Y, we find that this is the relation that we can have. So this part is completely dependent on small r, that is a real distance, and this part is completely dependent on this y. Y means it's dependent completely on the theta and phi part. And also this capital lambda, as we defined in earlier cases, is simply this expression form, which is dependent on theta and phi only. So with all this, since left hand side is dependent on small r, right hand side on theta and phi, so we put it equal to some constant theta lambda, and with this, and considering only this term, this particular term having minus sign, we get a relation like this, and we will call this as the angular part and this part as radial part, because the angular part means it is dependent on angles theta and phi, and radial part means it depends only on distance r. So from equation 7, and using this term lambda equal to this, we find a relation like this: capital lambda y is equal to minus small lambda y. And this is particularly an eigenvalue equation, where this operator L is simply to be given by this, and we'll see on the later course of time that this actually represents some L square by a square c square kind of things, and that's why this lambda is taken to be L into L plus 1. So with this, you can see that the angular part of the wave function, which is y as a function of theta and phi, is known as spherical harmonics, and it gives us an angle, is an eigenvalue equation 8, and with an eigenvalue given by equation 10, lambda equal to L into L plus 1. Okay, so, and we'll now see that we can now see that this part is completely dependent on smaller, and so this part will be called as radial part. So equation 7 now for the radial part can be written like this. Just making some kind of simplifications and putting lambda equal to L into L plus 1, we have a relation for capital R like this, given by equation 11. And we also note that we can separately solve this equation 8 as well as equation 11 also. Then coming to the next way how to solve it, we put Fr equal to R capital R, and putting this 12 in equation 11, equation will take a simpler form like this as given by equation 13. So whether equation 11 or equation 13, they are simply radial part of Schrödinger equation, and it's for a spherically symmetric potential. We see that potential is no longer dependent on r vector, it's dependent on simply on the magnitude of r, that is r. So if you look at equation 13 carefully, that this equation is almost same as that of one-dimensional time-independent Schrödinger equation, where the potential we can call it as effective potential as equal to Vr minus L into L plus 1 e square c square twice mr square. So this whole part, Vr minus L into L plus 1 e square c square by twice mr square, is nothing. It's representing a potential which is known as effective potential. So effective potential contains both the original potential as well as centrifugal potential. The second term is known as centrifugal potential in equation 14. So equation 13 now confirms that we can have a radial equation as a one-dimensional equation, and so it's become easy for us to solve the equation 13. So the analogy of 13 and this equation is definitely a boost for us to continue our journey in solving the Schrödinger equation while considering the radial part. So with all this, we are with some assessment here. And what do you mean by spherical symmetric potential? Simply, it doesn't depend on the direction of the distance. The potential is simply depends on the magnitude of the distance. Give two of the examples. The planetary motion as well the motion of hydrogen atom problem are examples. What happens to the TIC force has a potential? Write the TIC for it. So what is the TIC force has potential? In that case, we use the method of separation of variables with u, which is a function of r vector, is now u as a function of r, theta and phi, and separating out u, r, theta, u as a function of r, theta and phi in terms of capital R function of small r and y function of theta and phi, we can find out the Schrödinger equation for them. And also, so that for a spherical symmetric potential, a three-dimensional problem turns into a one-dimensional problem. So it's already shown here. Equation 13 is almost same as this equation, which means that that three-dimensional case is now turning into a one-dimensional case with a potential is as given by 14, known as effective potential. And then what is effective potential? And also the write the expression for centrifugal potential. So this is already given in equation 14. Effective potential contains the original potential plus the centrifugal term, and this part is known as centrifugal potential. So with all this, you can say that for a spherical symmetric potential, the Schrödinger equation can be expressed in terms of the spherical polar coordinate system, and we can separate out the solutions in terms of radial as well as angular part. Radial solution means it's dependent only on r, and the angular part, that is the spherical that is known as spherical harmonics, depends only on theta and phi. So this contains the angular part, that's why it is known as angular solution also. So with all this, I am ending up this video. Thank you very much for watching the video. Never forget to comment on our videos. Thank you once more.